Welcome class to our guided notes session on Skill 5 from Unit 5. This note outline that you have covers both Skills 5 and 6, which is solving both logarithmic and the harder exponential equations. This video will focus just on the solving logarithmic equations, and then our next video will solve the harder exponential equations. So this video is focused on Skill 5 from Unit 5. Okay, when you're solving logarithmic equations, there's two main types that you'll come across. The first one is when every single piece in the equation has a logarithm. So I kind of coined that phrase, all logarithms, the equation that has all logarithms. In that scenario, what you want to do is get only one log on each side. So it would look something like this. You'd have one log on one side and then a single log on the other side. So you get only one log on each side using properties of logs to condense. And then what you do is you set the inputs equal to each other so that it looks something like this. Whatever was inside each log before is now set equal to each other. And then from there you solve. Okay, so the reason why you can do this, you can get one log on each side and then just basically ignore the logs, is because of the one-to-one property of logs. That is what allows us to drop the log altogether and just set the inputs equal to each other. And the idea is this. So a logarithmic function, I'm just going to sketch the graph of the parent function. It has a vertical asymptote along the y-axis. It crosses the x-axis at the point 1, 0, and it kind of looks like this. Has that sort of shape right there. And this graph passes what we call the horizontal line test. Actually, it passes both the vertical and horizontal line test. The vertical line test is checking along the x-axis and making sure that for each x, if I were to envision a vertical line going through the graph, there would only be one point of intersection, indicating there's only one matching y value. That tells us there's only one y, one range value for each domain value. But to be one-to-one means the other way has to work as well. You need to be able to draw a horizontal line through any y value. So what this does is it checks along the different y values. So you kind of imagine these horizontal lines going through at each of the y values, and at each of the y values there should be only one point of intersection, which means only one matching x. And so because this graph of a log function passes both the horizontal and vertical line tests, what that means is there is always only ever one y for each x and vice versa, one x for each y. So right here, what you're looking at when you have an equation with one single log on each side, what you're looking at are two outputs, right? The log is equal to the y value, or the output. So you have one output here and then a different output over here, right? Because this was log base b of x, whereas this one is log base b of y. So these technically are different outputs, but then this equal sign is saying that they're actually the same. These two different y values are equal to each other. And so for a function that's one-to-one, like the log function is, if you have two outputs that are equal to each other, the only thing that could be true is if the inputs are equal to each other. There's no way you could have two different inputs, right? Two different x's that yield the same y value. There's just no way that could happen, right? This is one input over here. This is a different or seemingly different input, right? Because one's x and one's y. But actually, if the outputs are the same, then the inputs have to be the same. Why? Because the log function is a one-to-one function. There's only one output for each input and only one unique input for each output. So we utilize that property to our advantage, and once we get to this point where we just have one log on each side, as long as the base is the same, so that's another important part actually, the base has to be the same because it has to be from the same log function. So you have to have the same base, but once you get that, then you can basically drop the log altogether and just solve a simple, typically linear or quadratic equation from that point on. One thing you do need to be careful of though once you solve is to just make sure, check that your solutions would actually be in the domain for that function. Because remember, for a log function, So there's this vertical asymptote along the y-axis, and then the domain values, or the inputs, are always only ever greater than 0. So just check to make sure that your solution, when applied to the given problem, would satisfy the requirement that the inside of the log is positive. Okay, so that's really what this means. Make sure that the inside of the log, the input of the log, stays greater than 0. As long as that's the case, you're good to go. Okay, the other type of equation that has logs in it could be where not every single piece has a log. So some pieces have logs and some don't. In that scenario, what you want to try to do is isolate the log so that it looks something like this. You just have one single log, and you need to use properties of logs to be able to do that. And then whatever part didn't have a log, you would isolate that on the other side. So you'd basically get one log on one side and then one non-log, one regular expression on the other side. And then once you get there, you can rewrite that log expression into exponential form, which is this one here, using the definition of a log, which says that this little subscript b is actually the base of an exponential expression. The value inside the log, the input of the log, is actually the result, what you get after you raise that base to some power. And then whatever the log equals, the output becomes the exponent, right? We were saying that in our last video. The log is the exponent. Whatever the log equals is actually the exponent, should go in the exponent spot. So we can always rewrite a logarithmic expression in exponential form, remembering what part goes where. So the subscript is the base. The input of the log is the result. It comes after the equal sign. And whatever the log equals, the output of the log is the exponent. Okay, so then once you get to this exponential expression, then you just solve from there. Okay, so let's get started. Let's look at number 1. So number 1 would definitely fall along the option 1 category because both pieces have a log. And actually this one's kind of already down to step 2 because I already only have one log on each side. I don't need to do any condensing. And I can see that the log has the same base. So this is telling me that 2 outputs are the same. The only way 2 outputs could be the same is if these inputs are equal. That's the only way that could happen because a log is a one-to-one function. So I will basically drop the log part and just focus on the inputs. They have to be equal in order for the outputs to be equal. And so this is just a linear equation that I will just go ahead and solve for x. So I just subtracted 2x from each side, and I'll go ahead and add 5. And I get that x is equal to 6. And if I do a quick check and I plug in 6, I can see that both of the inputs would be positive. So I'm going to do 2 times 6 plus 1 on the first side, and then 3 times 6 minus 5 on the other side. So on the first side, I get log base 7 of 13. And then on the other side, this would be 18 minus 5 is 13. So it checks off, right? Log base 7 of 13 is equal to log base 7 of 13. Both of these inputs are positive, so they belong in the domain. This makes a true statement, basically. So x equals 6 is our solution. Moving along to example 2, I have a similar setup as example 1, but something a little different is going to happen here, and you will see why. So I've got one log on each side. It's already set up for me to just go ahead and isolate or set the inputs equal to each other. The base is the same, so that means it's coming from the same log function, a log base 12. And these are equal outputs, right? The equation, the equal sign here is telling me that this output is equal to that output. So the only way that could happen is if the inputs were equal to each other. And so then I go ahead and just solve that equation. So I subtracted x. Now I'm going to combine my numbers. I get negative 26. And then I will go ahead and divide by 2. And I get x equals negative 13. Okay, so that's my solution. But now I'm going to do a quick check to make sure that that solution falls within the domain of both of these functions. So that means both of the inputs have to stay greater than 0. So on the left, I have log base 12 of negative 13 plus 5. And then on the right, log base 12 of 3 times negative 13 plus 31. So on the left side, I get log base 12 of negative 8, because negative 13 plus 5 is negative 8. And then on the right side, I would have negative 39 plus 31, which also equals negative 8. So at first glance, it seems like, okay, these expressions are equal. The problem is, since the domain of a log is supposed to stay greater than 0, this value doesn't even exist. Log base 12 of negative 8, like if you plug that into a calculator, it would give you an error message because this value does not exist, and neither does that one. So you can't really say that two values that don't exist are equal. Like it just doesn't, there just is no such thing for equality for values that don't exist. So this is actually not a solution. And the reason why this happens sometimes is when you drop the log out of the problem and just turn it into a linear equation. Linear equations have domains that are unrestricted, right? The domain of a line is all real numbers. So these two lines can cross at any point. And in this case, they cross at a point where x was negative. But because these expressions are existing within a log, there's an added limitation, and both of these expressions have to stay greater than 0. And there is no place on either of these lines where they are equal. These lines do not intersect at an x value that's positive. And so there's no solution to this equation. There's no value for x that would allow the inside of the log to stay positive and then also make these outputs equal. So there's no solution. So always check your answer if you get one against the domain. See if it creates a negative inside the log, because if it does, then it's not really a solution after all. Moving on to number 3, it's another example that kind of falls along the option 1 category, but it's not set up yet where I can just ignore the log. I have to get one log on each side. So I have to use properties of logs here, and the first property I'm going to use is the power property to be able to take that coefficient of 2 that's in front of the log and make it an exponent of the 4 that's inside the log. So I'm going to rewrite that as the log base 6 of 4 squared. I can do the same thing with this coefficient of 1/3. Okay, so now I have minus log base 6 of 8. That was the inside of the log raised to the power of 1/3 because that was the coefficient of the log. So in both of those scenarios, I'm using the power property for logs. And so I can go ahead and simplify both of those expressions. That's the log base 6 of 16 minus the log base 6 of 2. Because 8 to the power of 1/3, quick review on that, is equal to the cube root of 8. And that is equal to 2. So this is what I have so far on the left, and then all of that is still equal to the log base 6 of x. And then because of this subtraction sign between them, I'm going to go ahead and use the quotient property of logs, which says that if you are subtracting two different log expressions, then when you combine the logs together, the inside parts of the logs actually divide. So 16 will divide by 2. So then I get down to here, log base 6 of 8 is equal to log base 6 of x. So now I got down to a point where I'm looking at the same log, right? Two different outputs for the same log that this equal sign is saying are actually the same, right? This is saying this output is equal to that output. The only way that could happen is if the inputs were equal, right? If x equaled 8. That's the only way these outputs could be the same. And because the only variable that was ever inside the log was just x, and x is a positive number, we know that this solution is in the domain, and so it is our solution. Moving on to example 4, this one, it kind of more matches the option 2 scenario, where not every single piece had a log. So what I'm going to do is get 1 log on one side and leave this 2 where it is. So I'm actually going to subtract this log expression to get it to the other side of the equal sign that has another log expression, and then combine the 2 log expressions. So I've got 2 on the left is equal to 2 times log base 5 of 10 minus log base 5 of x. And then I'm going to combine, I'll condense these log expressions into 1. So I'll make this 2. I'll move it and make it become a power of 10. And that makes it 10 squared. So this is log base 5 of 10 squared minus log base 5 of x. So 10 squared is 100. So now I get 2 equals log base 5 of 100 minus log base 5 of x. And then again, I have a subtraction between the logs. So that tells me that I'm going to need to use the quotient property. And the quotient property says that when 2 separate logs are subtracting and you want to combine them into 1 log, then you divide whatever is inside the logs. So the 100 goes in the numerator and x goes in the denominator as a single input for a single log base 5. Okay, now what I'm about to do is extremely important. So make a big deal about this step in your notes. Star it, highlight it, do what you gotta do to emphasize this in your mind. This moment is critical. This is what you do when you get to this point right here where you have 1 log on one side and a single number on the other side. What you do is you rewrite the expression into exponential form. So I don't know where you're sitting right now, but I want you to like say that out loud or mentally say it in your mind. Say it in just wherever you're at right now. I want you to say you're going to rewrite this expression into exponential form. This seems to be the hardest thing for students to remember. They seem to have an easier time solving equations where every piece has a log and they can get 1 log on each side and just drop the log. Students love dropping the log. Can't drop the log here, okay, because there's only one of them. So this is not a situation where, oh, 2 outputs are equal, just make the inputs equal. Like, that's not what's happening right now. Right now, we're saying that, okay, if I take 5, a base of 5, and raise it to a power of 2, it's going to result in this expression, 100 over x. That's what this expression is saying. That's the definition of a log. Whatever the log equals is the exponent, right? 2 is the exponent because it's what the log equals. So then what's the base of the log? 5 is the base of the log. So we're going to write it that way. 5 is the base. Whatever the log was equal to was the exponent. So it's going to become 5 raised to the power of 2. And then whatever's inside the log is the result of that raising of the base to the power. So 5 squared is 25. So now I get 25 is equal to 100 divided by x. And this is 25 over 1. So I need to get x out of the denominator. So I'm going to go ahead and multiply it to both sides. This is a little review of solving rational equations. Of course, it's a very simple one. So you could just cross multiply or whatever. But I'm multiplying by the LCM, right? The lowest common, or the LCD. The lowest common denominator from both fractions was x. I'm going to multiply x to both sides. On this side, it'll cancel. On this side, it won't. It'll multiply to the 25. So then I get 25x is equal to 100, and then that's a simple linear equation. I just have to divide by 25 to eventually solve for x. And so x is 4. X is equal to 4 is my answer to this question. And so let's check. Let's go back to the very original way that this was written and see if that makes sense. Okay, so we're going to check. Does log base 5 of 4 plus 2 equal 2 times the log base 5 of 10? Question mark. Well, I'm going to have to do some simplifying to figure that out. Or maybe I can use the help of Desmos, which is what I'm going to do now, to see if that's a true statement. So let's find out. So as you know, Desmos can also be used as just a regular calculator. So I'm going to use it here to help me figure out what the log base 5 of 4 plus 2 is. So I can just type that in there. Log base 5 of 4 plus 2 is this decimal right here, 2.8613 blah, blah, blah. Okay, that long decimal. So now what we're going to do is see if that is equal to 2 times the log base 5, 2 times the log base 5 of 10. And lo and behold, it is equal. Look at that. So 4 was the solution to this equation. Those two expressions from the original equation are equal when I plug in my eventual solution of 4. Okay, so I'll finish this off with example 5. In example 5, again, we have something that more matches the option 2 scenario where not every single piece has a log. I've got 2 expressions with a log and then 1 without. So what I'm going to do is combine these 2 expressions into one. I notice that they're being added together, so that tells me I'm going to need to use the product property for logs. The product property for logs tells me that if you have 2 separate logs being added and you want to combine them together, then you're going to need to multiply whatever the insides of the log were to each other. So the x plus 2 was the inside part and the x minus 4 was the inside part. So when I combine these logs together, I multiply those expressions. And then all of that is still equal to 2 on the right-hand side. Now, again, this is the part where students often forget what to do. So make a big deal about this part and make it stand out to you in your notes so that it's easy for you to find and it's easy for you to kind of remind yourself what to do. But once you get to this point where you have a single log on one side and a single value on the other, you rewrite into exponential form. Okay, and then you solve from there. So I want you to say that to yourself, either in your mind or out loud if no one's around. You're going to rewrite this expression into exponential form. So what does that mean? This subscript of 4 becomes the base. The log is the exponent. So whatever the log equals is the exponent of that base. So this becomes 4 to the power of 2. And then whatever was inside the log is the result. It's what you get after you raise the base of 4 to the power of 2. So then I get this. 16 is equal to x plus 2 times x minus 4. And then what you have is a quadratic equation. So this is another important part. This is now a quadratic equation. And it's also very important what you do when you have something like this. So how do I know it's quadratic? I know it's quadratic because when I FOIL these out, because yes, when you're multiplying 2 binomials together, you have to FOIL them. This is what I get. I get x squared. I'll do the rest in a minute, but that's why it's quadratic. It's quadratic because when I multiply these x's together, I get a power of 2. I get x squared. Okay, but then I don't only get that. I get x squared minus 4x plus 2x minus 8. And so what I'm going to need to do, because it is a quadratic equation, is I need to get 0 on one side, right? Get 0 on one side. We do this whenever we have an x squared in our equation. We need to get 0 on one side. So I'm going to move over to here. And I'm going to do this. I'm going to, well, let me rewrite it. So I have 16 is equal to x squared minus 2x minus 8 if I combine my like terms. I had 2 sets of like terms, negative 4x and positive 2. And when I combine them together, I get negative 2x in the middle. But then I'm also going to subtract 16 to both sides so that I can get a 0 on one side. So I get 0. And now this is equal to x squared minus 2x minus 24. Okay, so once you get here, you've got your quadratic equation on one side, you've got 0 on the other. Now we're going to factor. And if factoring doesn't work, we'll use the quadratic formula. But I'm going to try to find 2 numbers that multiply to c, right, negative 24, and add to b, negative 2. So I'm thinking of negative 6 and positive 4. If I add them together, I get -2. If I multiply, I get -24. So those are my two factors, x minus 6, x plus 4. And then you set each of those factors equal to 0 to get your two different solutions. This one would give me a solution of +6. This one would give me a solution of -4. But like with all solutions, we need to check them and make sure that they fit in the domain of the question. And the original question is all the way back here, so I need to check it with that original equation. So first I'll check when x was 6. When I check x equals 6, I get log base 4 of 8, right? 6 plus 2 is 8, plus log base 4 of 2 is equal to 2. Now this one I don't need Desmos for because we can evaluate these. Well, okay, maybe some of you would, or maybe we might need Desmos. These are a little bit tricky to evaluate, but they actually are both possible. This one here would be a 3/2 power because 4 to the power of 3/2 is equal to 8. And then this one here would be a 1/2 power. 1/2 power means the square root, and the square root of 4 is 2. Or 4 raised to the 1/2 power is 2. So yes, that does work. 3/2 plus 1/2 would equal 4/2, which is just 2. So 6 works and is a solution. So we're all good there. But you can also check this on Desmos. Okay, and then now we're going to check x is equal to -4. Okay, and when I do that, I get log base 4 of -2 plus log base 4 of -8 is equal to 2. Okay, now right off the bat, you should be able to recognize that that is not going to work because these values do not exist. There is no power of 4. There's no number I could raise 4 to and get a negative, right? It just doesn't exist. It doesn't exist. 4 raised to any power is going to be a positive number no matter what. So these values just don't exist. Therefore, 4 is actually not really a solution. See, for quadratic functions, which is this is a quadratic function, the domain is all real numbers. So there's no x that's off limits when you're solving those. But when you remember that this quadratic was the inside of a log, right? Before it became a quadratic by itself, it was actually a quadratic inside of a log, and that restricts it and makes it so it can only have positive solutions. So only 6 was the answer for that one. So pause your video here. I want you to try these U-tries here, 1 and 2. Do them and then revisit the video to check your answers. Okay, for number 1, you should get 9 for your answer. You can combine these logs on the left here using the product property. So then the 4 and the x multiply together. Then once you get a single log on each side, you can drop the log expression and just set the inputs equal and solve. And then check this answer. But this answer is in the domain because it's positive. For the second one, you should have gotten 4/3 as your answer in simplest form. That one is like option 2, where first you combine these logs on one side through the product property, so the 6 and the x multiply. Then you rewrite the expression into exponential form, so that's the key step. You take the base of 2, raise it to the power of 3, and set it equal to what was inside the log. And then 2 to the 3rd is 8, so then we know that 8 is equal to 6x, and then you just have to isolate x. Divide both sides by 6. And then these reduce because you can divide each of them by 2. So then you get 4/3 as your final answer. So that concludes this video on Skill 5. I will have a worksheet of these type of problems for you to practice tomorrow, and then they will show up on our quiz Friday. So if you're having any trouble with this or you have any questions at all, let me know and I will try to make sure I get those answered for you before the quiz Friday. Thanks. Bye.